Can we have the first slide? And this is the big question. The question is, low doses of radiation, are they dangerous? This is a book by Professor Burger that was written in 2000. And I'm going to try and answer this question for you today. Next slide. Well, the answer is that they're not dangerous. And this is rather surprising. Because if low doses of radiation were unsafe, then people who were having X-rays or having medical radiation treatment for cancer with moderate doses, and sometimes these doses are enormously high, organ doses of grades, would all be getting sick and developing cancer, and generally they are not. And if low doses of radiation were unsafe, then cancer rates in areas of the world where the background radiation is high would all be having higher levels of cancer than the low background areas. And many studies have shown that they're not. Next slide, please. But of course, we can also say that they are dangerous. Because if low doses of radiation are safe, there would be no health effects like those associated with the Chernobyl effects that we've already seen Professor Musso talking about in the animals and in the birds. And as far as the human race is concerned, of course, enormously high levels of radiation damage and effects on health that we have seen in the many papers that have been published from the ex-Soviet Union territories and even from Sweden and from other parts of the world. And I myself have studied these effects near Sellafield, and there are now emerging thyroid cancers near Fukushima. I'm involved in a big radiation case in America, near Los Angeles, in a site called Santa Susana. We have seen effects from very small doses in atmospheric test batteries, nuclear test batteries. I've studied the Irish Sea, I've studied the Baltic Sea, small numbers of childhood cancers near nuclear sites, breast cancer near nuclear sites. I can go on and on and on. And of course, the effects that I've studied in Iraq and in the Balkans related to internal radiation affecting uranium weapons. Next slide. So we have two answers to this question, and actually they're both correct. So there's something very wrong here. And what is wrong is the question. The question is at the very heart of the whole issue of radiation protection. And it's something that has been overlooked either by error or on purpose since 1952, when radiation protection began with the International Commission on Radiological Protection. Next slide. It's the concept of absorbed dose. I noticed that Professor Musso is fitting external radiation dosimeters to animals and to birds, and measuring millisieverts, microsieverts per hour dose rates. But these, of course, are external doses, and although they may well correlate with the internal doses, this is the doses received by animals and by humans as a result of ingesting or inhaling radionuclides, it's not the same thing. And the concept of absorbed dose is the primary problem. It is the basis of all radiation risk legislation, and as I will show, it's a misapplied scientific concept adopted by the military in the 1950s, and now employed to justify nuclear energy and the use of uranium weapons and a whole range of issues which actually are resulting in the deaths of millions of people across the world, and having untold damage on the ecosystems of the planet that we live on. Next slide. Now let's just talk about what we mean by low dose. My operational definition in terms of conventional dosimetry, that's the one that's used at the moment. So if you went out with a Geiger counter and you weighed it about, and you asked it what the dose rate was, we would be talking about any dose up to about natural background, say maximum 5 millisieverts in a year, this would be, or a dose rate of about 100 nanosieverts per hour. Now the industry's definition is much larger, it's anything below around about 100 millisieverts, and it's regularly said that there is no possibility of showing that there's a significant cancer effect, statistically significant cancer effect in any population at levels of exposure below 100 millisieverts. Of course, this is only done because if they do find an effect, they say it cannot be due to radiation. So they, if you like, put the argument on top of its head. Misunderstandings about this quantity of absorbed dose here are fundamental to the understanding of health effects of exposure to radionuclides and to radiation in areas from Fukushima to Chernobyl and from the test veteran sites and people who live near nuclear plants. And of course, the many areas of the world where there's contamination as a result of historic pollution. For example, at the moment, the Baltic Sea, which is the most radioactive sea in the world, and the Irish Sea, which I've also studied. Next slide. Now, we'll give a couple of examples of these quickly. The United Nations Action Plan was based on scientific studies from the 2005 Chernobyl Forum. The Chernobyl Forum noted that the Chernobyl nuclear accident was a low-dose event. And it stated as a result of this that the vast majority of people living in contaminated areas are in fact highly unlikely to experience negative health effects from radiation exposure and can safely raise families where they are today. In Belarus, the UN wrote down that the dose to the population of Belarus was less than 2 millisieverts. This is approximately equal to natural background radiation in that country and in my own country, in England and Wales, 2 millisieverts. Of course, we know from the massive amounts of work done by LHC and its colleagues that the reality is very different and that the health effects in these therapies have absolutely collapsed, increased massively, and the health has collapsed. Next slide. And Fukushima, of course, the same sort of thing has been done. UNSCEAR and IAEA and the World Health Organization stated that radiation exposure following the accident poses no immediate health risks, and the long-term health risks are unlikely because the dose is low. But of course, we already have seen what these low doses have done to the bird populations, and in fact, very recently we've learned that 44 childhood thyroid cancers have now been diagnosed amongst 178,000 people who were tested, which gives an approximately an excess risk of about 150-fold, between 80 and 150-fold. So something certainly has happened. But what did happen was that the WHO are saying that these cannot be caused by the radiation because the doses were too low. According to the World Health Organization, the maximum dose of the thyroid in the Fukushima territories was about 30 millisieverts. Next slide. And of course, the same sorts of arguments are advanced for the development of nuclear waste repositories, like the one in Sweden, which was proposed, one in Finland, and of course one in Canada that I'm talking about. They say that the drinking water dose would be a factor of 100 without regulatory criteria. This is dose. We're always talking about dose, dose, dose. Next slide. Next slide. So let's have a look at some doses. Well, here's a range of doses written up on the website of the Health Protection Agency, the radiation protections in the UK. You can see that the doses from X-rays are small, and you go up to CT scan, 1.4 millisieverts, and the chest scan by CT is 6 millisieverts. You go all the way up, and you can see that the unmeasurable bulk changes are found at 100 millisieverts, and this is the same level that no cancers can be predicted from, according to the Health Protection Agency, and so on, up to the very high doses of 5 sieverts, where half of the population receiving a whole body dose of 5 sieverts would die. Next slide. But the problem is this, and this is the essential problem that everyone has to see, that dose is an average quantity. It's the amount of energy translated, absorbed from an external radiation field into a kilogram of tissue in joules. So you measure the amount of joules and you divide by the mass in kilograms and you get the dose in grays or in sieverts if you're looking at alpha particles. But you can see that there's a problem with internal radiation. If you look at this, the picture on the left, which is from a paper which I've just managed to, with great difficulty, get published, and if anyone is interested in this issue, you must go there and see this paper, because a lot of what I'm saying here is written down there. And you can see that you could have, you could get the same dose from sitting in front of a fire and warming yourself. We're talking about thermal dose now, and it is energy per unit mass we're talking about. Or you could reach into the fire and use a hot coal. And there are situations, as far as internal radiation is where there's a very And the part of the body that's significantly important that we're talking about is the DNA, the chromosomal DNA inside the living cell. Next slide. So this is the paper. If anyone wants, they can get a note of it afterwards from me, or they can take a photograph or whatever. So all of what I'm saying here is going to be inside this paper, which is a 50-page article. It's all there, and I'm going to talk a bit about it now. Next slide. So here is one example of the hot coal analogy. This is a plutonium particle photographed in a rat lung, and you can see that a lot of energy, those little star-shaped things are the alpha tracks, which have a range of about 4 cells. And this is called an alpha start. So you can see one part of the lung gets a very large dose, another part gets no dose, and the overall dose can be very small. So this could be called a low-dose event. But as far as the cells are concerned, it's not a low-dose event. Right, next slide. And this is a small hot particle from the Irish Sea embedded in an edible mussel, an invertebrate. And you can see that these little tracks here represent the alpha decays. So next slide. So what are these alpha decays producing in terms of dose? What sort of dose does the cell see in these low-dose situations? Because these low-dose situations can be really, really tiny doses, but the cell doesn't see really tiny doses. What the cell sees are quite big doses. A single track from an alpha particle through a cell produces approximately 380 millisieverts. That's certainly not a low dose. That's a very large dose. That's a cell-killing dose. Then for sequential decays, if you take the radium-224 decay series from thorium-228, you're getting 1.5 sieverts into the cell. And if you happen to inhale a hot particle from plutonium-239 in the Irish Sea or in the Baltic Sea, you're getting a dose to the cell of 570 millisieverts per minute. So that's half a sievert per minute to the cell. Of course, it kills the cell. Or you get a warm particle, what I call a warm particle, which is like the uranium particles produced on the battlefield in Iraq, where studies that I've done with my colleagues have shown massive increases in cancer. In Fallujah, 30 or 8-fold excess in leukemia in young people there up to age 34. We're getting 4.4 millisieverts per day. Again, very, very large doses. Next slide. And these large doses from the thorium series, the radium-224 series, have in fact been studied. But they have been studied only with regard to the cancer-producing effects that they produce. And of course, if they kill the cells, and if they kill the people, they're not going to produce cancer. And here we have a graph which I produced from a paper from Murray studying the thorotrast, which is an internal exposure to radium-228. And you can see for the women here, they all die before they get cancer, the ones that have been treated with thorotrast. So these are very, very large doses, and they kill a lot of cells, and they cause effects. But mostly, in terms of the radiation protection agencies, they would be characterized as small doses, as low doses. Next slide. And of course, many of the materials coming out of Chernobyl and Fukushima were in the form of these particles that I'm talking about. Particles that produce very high doses to small cells. This is an autoradiograph of a skirt, a piece of clothing that a woman was wearing. She came back from Kiev shortly after the Chernobyl accident, and her dress was put on top of a photographic plate, and you can see the particles there. Next slide. And this is a very recent paper published last week by some Japanese people who did a similar sort of thing and looked at cesium-loaded particles that they trapped in air filters. And you can see the same sort of effect as particles here. And they actually looked at the particles, because nowadays we have all sorts of scientific equipment that can look at particles. Next slide. And what you can see in these Fukushima particles here, you can see that these are actually cesium-laden particles. They're about 2 microns diameter, the ones that they get trapped here. Of course, smaller ones would have gone through the filter. And the activity of the particle is 2 becquerels per particle. So if you have a particle like that in your lung, it's producing 2 decays per second. And this is just cesium-137 that they measured. But in fact, if you look at the spectrum, the ESCO spectrum, they have a great deal of lead in these particles also. Now, of course, lead has a low melting point when the explosions occur, which correlation with the dose to the DNA, because it's now universally conceded that the problem with radiation is that it causes mutations to the DNA. These are the consequences of this are the effects that we have seen just now. And Professor Muller showed us the pictures of the birds and all the genetic damage there. It's genetic damage that we're talking about. And so the target is not even the cell, it's the chromosome and DNA, and therefore it's the dose of the DNA that is relevant for radiation protection. And so this takes us to a number of other ways in which internal radiation is different from external radiation. Because if you have external radiation, you average all of the tracks over all of the cells in the body, and so the DNA dose will be an average of all of the ratio between the number of tracks that there are in any mass of tissue and the amount of DNA in the same mass of tissue. But the situation is quite different for certain radionuclides which have chemical affinity with DNA. Now, the people who are in the radiation protection community do not seem to be chemists, and they do not seem to be biochemists, they seem to be physicists. And as far as they're concerned, the human body or the body of any animal consists of a bag of water into which they can dilute energy. They're not concerned about what's inside the water. So what we are concerned about is what is inside the water. We're concerned about the target for this effect, which is the DNA, and these are the DNA dimensions here. Next slide. Now, all radiation effects, even external radiation effects, as I said, are delivered as tracks of different lengths depending upon the energy, depending upon the type of radiation. For photon radiation, the tracks are reasonably long, about 400 nanometers or more, 400 microns or more. But for internal radiation, it can vary depending upon the situation, depending upon the particular kind of radiation, depending upon the source of the radiation, and depending upon the radionuclide. So I mentioned you managed to do some mathematics which showed the ratio, that the probability of DNA being hit by a track in terms of the distance of the radionuclide that is decaying. And you can see that for any radionuclide in the cytoplasm, so reasonably far away, remember this is a 10 micron cell that I'm modeling here. So you have to get within about 50 nanometers before you start to see an increase in the probability of hitting the DNA. Next. So there are a number of ways in which you can get genetic enhancement from DNA ionization from internal exposures. And I won't have time to cover all of these today, but I have described them all in that paper that I earlier. One mechanism is, of course, DNA affinity. So if something is bound to the DNA physically or chemically, then it's sitting right on top of the DNA. So of course, if that's the case, it has a very much higher probability of hitting the DNA than if it's somewhere far away from the DNA. So in other words, if this is a radionuclide and it's sitting on my head and I'm the DNA, then it's going to have a much bigger probability of hitting me than if it's about 100 yards down the road, which is approximately the correct interdimensional relationship. Then, of course, there's one that's absolutely never considered, which is transmutation. So, in other words, if you have carbon-14, and there's an awful lot of carbon-14 comes out of these situations, and it's bound into the DNA, then, of course, when it decays, it turns into nitrogen. So that's going to cause an effect on the DNA, absolutely 100%. Then there's a secondary photoelectron effect, and this has to do with the absorption of gamma background by elements, which is proportional to the fifth power of the atomic number. So obviously, if you have a very large element with a high atomic number, like uranium, platinum, or gold, or lead, you will get very much bigger focusing of the external gamma radiation into the body than you will if you just have water, which is how it's normally modeled. And of course, if that radionuclide is also bound to the DNA, which uranium does do, it binds very much onto the DNA, then it's going to have a focus external background radiation into the DNA. And there are various other methods in which we can enhance radiation from the internal. One of them is these hot particles, which I just mentioned. Next slide. So I'm going to say a few words about transmutation, because it's something that has never really been considered in radiation protection, although it should have been. As I said, carbon-14 can be absorbed into a whole range of biological substances in the organism, changes suddenly into nitrogen. You've got tritium, which exchanges with all the hydrogens, and of course we're mainly composed of hydrogens. A lot of the chemistry in our body is a result of hydrogen exchanges. If that's tritium, it suddenly changes into helium, and it introduces an ionization, 100%. Then you have sulfur-35, you have iodine, and you have phosphorus-32. All of these are intrinsic and basic building blocks for the materials which life uses and is developed using over evolutionary timescales. And we have a whole new load of these things now, which are enhanced as a result of nuclear energy, as a result of accidents and nuclear explosions in the atmosphere. And these substances suddenly change into different substances. Well, that's not very good. In fact, Pauling originally was in Sakharov also in 1959, argued that as a result of the increasing carbon-14 in the atmosphere because of the weapons fallout, it would introduce an enormous amount of mutations into the human race, and probably he was right. Next slide. Now, this is not something that is magical or is unknown. A lot of work was done on transmutation in the 60s. I'll give you one example. Two Frenchmen, Appelgöl and Lataget, in 1962 published a fascinating paper where they incorporated carbon-14 into some bacteria. And because carbon-14 has quite a weak utility, they left it in a refrigerator for a whole year. And then they compared it with the same amount of dose delivered externally, also by carbon-14 suspensions were placed next to it. And they found that there was 160 times efficiency, lethality, from the incorporated carbon-14 transmutation effect compared with the external radiation from the beta particles from the carbon-14. And this has been in the literature since 1962, but of course none of the radiation protection agencies have done anything about it, and incorporated it into radiation protection. Next slide. The secondary photoelectron effect, something that I have studied. This is from my student at the University of Ulster, Andres Elsaesser, who has looked at the enhancement of background radiation by different elements. And what we have here on the left here is water. There we are. This is a sphere of water, you can't see it. And this is 100 times, we were bringing in 1,000 photons here. No, 10,000 photons, 100,000 photons, sorry, 100,000 photons. So external radiation is coming into this water, and this is the number of little electron tracks that will be generated as a result of this. This is a computer program developed by CERN. And then this is gold. Of course, gold has a higher atomic number, 72, so that's going to create more photoelectrons. And there's uranium on the right. Those are the photoelectrons from uranium. And the effect of that is going to mean that if you have an uranium particle of that size, which is a small size particle in your body, it's going to enhance the effect of the natural background radiation by producing all of these tracks very close to it. And of course, if it's bound to DNA, it's going to smash the DNA to pieces, which is why we find high levels of chromosome damage in uranium miners, and also in people that are exposed to uranium in battlefields. And very recently, as a result of a paper by Gisela Cano in America, in France, she found very high levels of cancer and heart attacks in uranium workers for AREVA. Next slide. And also, it's recently been discovered that most of the radiation effects of cancers that were produced after Hiroshima are associated with people who were exposed to the black rain. This is rain that fell after the bomb and contained uranium particles. There's a group in Japan at the moment working on this. And this includes people who were, of course, in the control group, so they were not inside the city at the time of the bomb, but they were just rained on by the fallout at distances of 5 miles or more. Next slide. So this brings us back to where I began here. And it's a very important point, is that people who are studying radiation and people who are studying the studies of people who are studying radiation should not be concerned too much about the concept of dose. Because you have to be very careful about whether it's external or internal dose. It does seem as if certain internal doses attract a hazard enhancement factor, if you like to see it like that, which is very large indeed. For example, if you take children who live near nuclear sites, and now they're excesses. You could not possibly say that those doses, and it's possible to calculate the doses, are going to be higher than about 100 nanosieverts, but a tenth of microsieverts, about a tenth of millisieverts maximum. Even the most polluted sites like Sellafield, not more than about 200 microsieverts, which is very much smaller than the natural background dose. So in order to account for those, you have to add a weighting factor to the internal exposures in order to explain them. And in fact, we have done this. So next slide. So I represent a group called the European Commission on Radiation Risk. Alexei helped me to start this way back in 1998. And it has a website here where you can download the latest recommendations. And if you want to know pretty accurately the consequences of any radiation exposure, you can use this model where we have a system of weighting factors for each radionuclide exposure. So, for instance, for strontium-90 as a result of its affinity for DNA and as a result of studies that we have made of strontium-90 effects following weapons fallout, we can put a weighting factor on it of about 300. So if you get 1 millisievert from strontium-90, then you multiply it by 300 and it becomes 300 millisieverts. Next slide. So I'd just like to finish off now by saying that the European Committee on Radiation Risk would not have existed without the involvement and support and enthusiasm of Professor Alexei Ablakov, my friend and colleague in this affair. It has been extremely successful, this book, this study, and this model, and it's won several court cases, and I'm sure it will win a lot more. So if there's any way in which we're going to make the world a better place, it's by getting behind an independent group of scientists who study what's really going on, rather than just inventing their own nonsense relating to the concept of absolute dose. So thank you for inviting me here, and thank you for listening.
Мы сейчас заслушаем последний доклад профессора Московского государственного университета Сергея Николаевича Бобова.